All right. Hello, good morning, everybody. I hope you are having a good day. Today we'll try and finish Module 6 para mabigyan kayo ng enough time to finish homework homework 6. And as I've mentioned last time, homework 6, medyo 3 problems lang siya, pero it might take you some time to finish them. Kasi medyo mechanical sila. Do not count on them just being 3 items. You'll wait until the last day of the deadline to finish and cram it. So perhaps you'll need 1 day or two. Though I haven't personally answered the problems, but I estimate that you'll need some time to finish it. Though ang burden sa homework na to is not on proving. So ibig sabihin you'll do actual work more than just thinking about what to do, just as like what you're doing when you are proving. So try to work on the homework as early as possible. So the deadline is on Sunday, August 8th, right before midnight, so that you can get the markup. And then for those who still have some requirements, some past due homeworks, the deadline would be on August 9. There would be no extension for that. The reason is that so that I'll have enough time to finish grading them before the submission of the grades. And then last day of class is August 9. I'll give the final homework, which will be homework 7, which will be due on the finals day. So I'll check that on the calendar, but it's sometime, I think, sometime before August 15. I'll need to check the exact date, but yeah. But don't worry, it will just take you 1 day to finish or less to finish homework 7. And then once you submit homework 7, I'll try as much as possible to send you my proposed final grade for you, or my computed final grade for you, so that you'll have a little bit of time to think it over and consult with me about the final grade. If you think you deserve higher or you think you should get lower grade, so just let me know via email and then we can discuss there. But yeah, I'll need some lead time to finish grading the last few homeworks and giving you the final grades, right? But of course, I'll do it right before the deadline. I'll do it definitely before the deadline, and I will just upload your final grades at the deadline. So para if you still have some questions, I can address them. Okay, back to module 6. I think last time we looked at the Gram-Schmidt orthogonalization process and noted some things about it. Number one, if you have a linearly independent set, we said those vectors or those elements of the set are not necessarily orthogonal to each other. So, and we said that orthogonal bases are usually the best bases for numerical purposes. So that's why people prefer orthogonal or even orthonormal bases instead of regular bases. So we said any linearly independent set or any orthogonal set is linearly independent, but the converse is not true. There are linearly independent sets that are not orthogonal. And one main result of linear algebra is what we call the Gram-Schmidt process. Let me just browse up to see the Gram-Schmidt process. So the Gram-Schmidt process is the input algorithm is a linearly independent set. And what we get out of this linearly independent set is an orthonormal set. So remember, when we say an orthonormal set, it is a set that is and the length of each element of that set is equal to 1. All right. And you see how simple the Gram-Schmidt process is, at least the classical one. So we start with, a little by or one by one, creating the elements of the orthonormal set, the QJs. So we start with A1. What's happening? We start with A1, and then we normalize A1. That's going to be our Q1. And then for J going from 2 to N, we will try to construct the QJs so that QJ will be orthogonal to Q1, Q2 until Q sub j minus 1. So how do we do that? Well, we consider AJ. Of course, AJ is part of the planning process to get the QJs, but we subtract from it the sum of inner products times the existing QJs in the set. So, ito yung dahilan kung bakit na-preserve natin yung span ng vector spaces because we keep on considering the QJs or the AJs along with the Q sub j minus 1 until Q1. So, ganyan nangyayari. So, you can think of this as a triangular orthogonalization. Kasi nangyayari ay we are creating an orthogonal set. And then along the process, you will see later that we are doing it via a right triangular matrix. But that's going ahead into the next topic. But yeah. The classical Gram-Schmidt process provides us with a very neat formula. And in theoretical discussions or in theoretical.
Sir, medyo nawawala po yung boses nyo.
The arithmetic operations in this formula that you see are arranged in not a good way or not in a way where the round Yeah, sorry guys, na-drop ako. So, mas mabagal than usual pa yung internet ko ngayon. Let me try another net. Okay, I hope this one's better. But anyway, as I was saying, almost never ginagamit yung classical Gram-Schmidt process in performing numerical calculations because the operations in the classical Gram-Schmidt process are arranged in such a way that round-off errors accumulate or they pile up on each other. Right? And one remedy to that is to use the modified Gram-Schmidt process that we have illustrated yesterday, the other day as well. So what it does is that it keeps on updating the vectors that we use for the orthogonalization. So you start with the AJs, and then we set the AJs to be the vector VJs. And then why the change of variable? Because at every step of the way, as we construct the QJs, we will be updating the VJs that we are using. Ibig sabihin, sa bawat iteration ng algorithm, ina-update natin yung mga VJs na hindi pa nagagamit. So this method apparently takes care of the numerical instability of the classical Gram-Schmidt process. But the thing about algorithms 1 and 2 is that they are equivalent, meaning on paper or on a perfect machine, they should produce the same orthogonal set or orthonormal set. However, once you rely on computers to do the calculations for you, there are rounding offs because computers are nothing but finite machines. They can only accommodate a finite number of decimal digits or a finite number of significant digits. So even though by design algorithms 1 and 2 are equivalent, then in a machine implementation, we might still get different results from these two guys. But whenever doing calculations via a computer, algorithm 2 or the modified Gram-Schmidt process is more reliable than the classical ones. That's why almost every algorithm ginagamit lagi, or almost any numerical technique always use the modified Gram-Schmidt instead of the classical one, right? You'll be doing the Gram-Schmidt process in problem 1 by hand. So I think I explained last time what you need to do to that homework problem. But today we'll talk about a nice application of the Gram-Schmidt process, or in particular, an application of orthogonalization and unitary matrices. And that's what we call the a QR factorization or QR decomposition. So we say here that since the Gram-Schmidt process will give us back a set of orthonormal set, right, or a set of orthonormal vectors. So we can use those vectors to form a unitary matrix, especially if um, the dimensions agree. So kung meron kang Q1, Q2, Q until Qn that are orthonormal to each other, then we can use these Qj's to be the columns of a matrix. Okay. And I guess last time in one of the remarks we have shown that if the Q if the QJs are orthonormal, then the matrix formed by using them as columns is a unitary matrix, and that is a very efficient result, or a very useful result, because in most of or actually in all of linear algebra, perhaps matrix inversion is one of the most expensive processes. So solving for the inverse of an invertible matrix is a very unstable and very expensive computational routine. So if we have a nice expression for the inverse of the matrix, it will save us a lot of time in performing our numerical calculations. For instance, unitary matrices very very in demand for numerical purposes, because remember, if you have a unitary matrix Q, its inverse is just its adjoint, right? And finding the adjoint is not that costly, at least computationally, because all you need to do is take the matrix Q, take its conjugate transpose, and you get Q adjoint or Q star. And that adjoint matrix will also serve as your as the inverse for Q. And we all know that if you know the inverse of a matrix, solving linear systems with that coefficient matrix is very will be very easy, because all you need to do to solve say ax equals b, you can apply the inverse to both sides to get the unknown vector x, right? So ito lang yung general nating formula for solving linear systems. This is very nice if you know a nice way of computing the inverse, or if you know the inverse explicitly. However, most of the times, as I've mentioned, this is computationally expensive when you try to compute A inverse, and also it's very numerically unstable. All right. So that's why we will take advantage of the fact that we have now learned a way to construct a unitary matrix. All right. And that will hinge on having a QR factorization or a QR decomposition of a matrix A. This is just saying that we can write A as a product of two nice matrices. So if you have an M by N matrix A, we say a QR decomposition of that matrix A is Q times R. So we are simply factoring the matrix A, or writing it as a product of two matrices. But not just any two arbitrary matrices, but two nice matrices. Okay. So the matrix Q here, that is the left multiplier, is an M by N matrix. It's a square matrix M by N that should be unitary. And you see why I love the QR decomposition, or why people love QR decomposition. It's that because the unitary matrix Q has an explicit inverse. Its inverse is again just its adjoint. Right? So hindi na ganon kamahal yung pagko-compute ng Q inverse if you know that Q is unitary. And there's an added bonus to it because the matrix R, which is m by n, so that we get back our m by n matrix A, this should be right upper triangular. So when we say right upper triangular, ang meron lang non-zero entries possibly are those Rij's wherein I is less than or equal to j. Okay? Or in other words, if you have a right upper triangular matrix, then Rij must be equal to 0 if the row number is greater than the column number. So that matrix R will look like this. Siyempre, may diagonal entries ka dyan. Diagonal 1, diagonal 2, until the last diagonal entry here, let's say dn. And then dito magkakaroon ka rin ng laman, say f1, f2, f3. So there are non-zero entries here. That's why it's called right upper triangular or right triangular. Ang may non-zero entries lang ay yung upper diagonal. And the rest, the entries below the main diagonal are all zeros. So that is what is meant by being a right triangular matrix or an right upper triangular matrix. So ang may non-zero entries lang possibly ay yung diagonal entries at yung nasa ibabaw. Everything below the main diagonal is equal to 0. And you will see na it's very easy to compute linear systems wherein the coefficient matrix ultimately reduces down to a right upper triangular matrix or a right triangular matrix. Actually, I guess here it's a little bit redundant to say right upper triangular. So either we say right triangular lang or upper triangular. So I think that is understood in literature. So let's just call it right triangular para ma-justify yung paggamit ng capital R for the name in the decomposition. So Q is unitary, and then R is right triangular. Okay. Nice result, theorem 43. Every matrix has a QR factorization. And one way to prove this is to argue that the Gram-Schmidt process, which applies to any linearly independent matrix, applies to any m by n matrix. So, meron ka lang intermediate trick na gagamitin. You first try to show to ignore non-linearly independent rows or columns on your matrix A, and then apply the Gram-Schmidt process on the linearly independent one, and that will give us the unitary matrix Q. Okay. Now I omitted the proof because again I promised that module 6 will be more computational. So don't worry about that. I just put theorem 43 here just for the sake of the result itself. So that means that any matrix can be, or any system of linear equations can be solved using QR factorization. Kasi lahat ng matrix ay may QR factorization. And I guess I already hinted about it in one of the things I said earlier. Now, the Gram-Schmidt process will actually give us the matrix Q. Okay, so if you begin with a matrix A with linearly independent columns, you simply need to apply the Gram-Schmidt process to it. You'll get back a unitary matrix by using the results of the orthogonalization process as the columns of the matrix Q. Now, the matrix R actually are computed along the way. These are the inner products that you use to that we use in the subtrahands in the second step of the classical Gram-Schmidt process. So, kaya sabi ko kanina, the Gram-Schmidt process is actually a triangular orthogonalization of a matrix A because it gives us an orthogonal matrix through the use of entries coming from a right triangular matrix. So I'll show you later that in the code that I provided to you in the Matlab scripts that I provided to you with the module,
you can also get the matrix R out of the Gram-Schmidt process, or those internal functions for the Gram-Schmidt process. Okay. Now, in particular, if you go back to this Matlab file, ex65.m, makikita nyo yung line 5 doon, it outputs two matrices. I think the code there was you have QC, comma, RC equals Gram-Schmidt of A. All right. So again, if you call GS of A, which is an internal function found at the end of the Matlab script, this syntax just tells us that it will return two things, the matrix QC and the matrix RC. The matrix QC actually is the unitary matrix whose columns are the result of the Gram-Schmidt process, and RC is the right matrix, the right triangular matrix in the QR decomposition. So that means when you run the GS function in the Matlab script I provided, it will already give you the unitary matrix Q and the right triangular matrix R needed in the QR factorization routine. Okay. And similarly, in the modified Gram-Schmidt code that I shared with you, there are also two outputs to it. You get QM, the unitary matrix, and RM, which is the right triangular matrix. So we'll go back to ex65.m later. But one good check if we have a nice QR decomposition, or by the way, the QR decomposition is not unique. You can factor your matrix into, or is it not unique? I guess there are several ways on how to do the QR factorization, right? So the Gram-Schmidt process is just one of them, right? But again, we don't trust all calculations done in a computer, so that usually every step of the way, especially if you have a very big code that you're running through Matlab or any program that you like, we always put sanity checks along the way. And one sanity check that we can do is to compute this norm. So what does this norm compute? So QC times RC minus A, so it is just computing how far is our QR factorization from the actual matrix A. Because again, we wanted that A be written as the product of QC times RC, right? A unitary matrix times a right triangular matrix. So QC and RC are given to us by our Gram-Schmidt process. But to make sure that we have the right QR factorization, or to a close to correct QR factorization, we can ask Matlab to compute the discrepancy. Using RC, we expect A to be the answer. So compute the error here. So QC times RC minus A is the error in the QR factorization. And let's measure how big it is. So we measure it via the L2 norm. So this will give us an idea how good the QR factorization is, so that we can have an idea of the expected results. Are the results reliable or not? Okay. So once you have run ex65.m, so QC, RC, and A are already in your workspace, so Matlab already knows them. So you can just type this guy or this syntax into the command window and then press enter. And then it will give you the size of the error. Okay. So if you do so, if you have your Matlab running in front of you, you can run ex65.m using, I think this is the 5x5 Hilbert matrix, and then run that. Then in the command window, type this guy, and you should get 10 to the minus 16, or a number that is a factor of 10 to the minus 16. Okay. And then the same thing will happen if you compute the error using the modified Gram-Schmidt process, or using the modified Gram-Schmidt process to get a QR decomposition. So we got QM already computed by MGS, RM already computed by the MGS routine. This is the discrepancy or the error between the QR factorization that we got and the actual matrix A, and then measure how big this error is. then I guess you'll also get a number that is a factor of 10 to the minus 16. So this shows that up to machine precision, both the modified and the Gram-Schmidt process provided an accurate QR factorization. Okay. Pero don't be misled by this good results for the QR factorization, because I think we have seen last time that the Gram-Schmidt process on itself is very unstable and unreliable, that QC is not near a unitary matrix. So kaya dalawa yung check natin dito. How good is the QR factorization? And the second check is, do we really have a unitary matrix Q? Kasi yung problema, nakita natin last time, nung ginawa natin yung Gram-Schmidt process on a computer, we did not get close to a unitary matrix. When we computed, I think, when we computed the norm of Q adjoint times Q minus the appropriate identity matrix. So in the the classical Gram-Schmidt process, I think we got a big number here, or a number that is nowhere close the machine precision, which is 10 to the minus 16. All right. So we'll play with Matlab towards the end of the class. So I'm just laying down the theoretical concepts first. All right. Now, another way to get a QR factorization is via the householder algorithm. Now, the householder algorithm has a very nice geometric interpretation, because the matrices, the householder matrices, could be perceived as rotation or flipping of matrices. But unfortunately, we don't have the luxury of time to go over the nice geometric interpretation of the householder algorithm. So if you are interested in knowing these facts, you can consult the book by Trefeten and Bao. I think it's in their lecture 10. Or you can just Google householder transformations, and you will see the geometric interpretation of householder matrices. All right. But for us, our main concern, insofar as householders or householder matrices are concerned, is on how this method can give us a QR factorization. All right. But in order for us to study householder in a more efficient way, we will introduce some notations here. Actually, these are Matlab style notations. So we define what this matrix means. So you have a matrix A, and then inside parentheses we have this guy and this guy. So when you type into Matlab, say A of 1 to 3, and then 4 until 7, right? So this, what Matlab will do is it will harvest certain parts of the matrix A. Specifically, Matlab will consider the first until the third row, and then the fourth until the seventh column, right? So kung gagawin nyo, halimbawa, B equals A, maybe I should write it down like this. If you call B to be the matrix or the submatrix of A from 1 to 3, 4 to 7, so you're using columns there. So this will give you the submatrix consisting of the first to third rows and fourth to 7 columns. So i-ignore nyo na yung ibang entries. So as a result, this matrix B will be what? It will be 3 by 4. Kasi consider nyo lang yung submatrix of A from the first to the third row and fourth column to the seventh column. So ganyan, pwede nyo gamitin yan kay Matlab, and that's what I adopted here in discussing the householder QR factorization algorithm. So yeah, so that's how this notation works. When you have a single number, say here, you just have a single number, say 4, you will get a vector or a matrix in only one column. Hindi nag-update yung screen ko. There you go. So this will give you the submatrix of A consisting of the first until the third rows, but only the fourth column. So ibig sabihin, ito ay 3 by 1 matrix lang. So if there's a single number, that means it's just a single column, or that is just that single column. When you use just a colon there, instead of a number after the comma, you just use a colon. That means you are considering all columns. So this matrix B will be the submatrix of A, consisting of the first until the third row, and then all of the columns are included. The same thing goes if I have a colon here, and I have, say, 5 to 8 here. So this will give me the submatrix of A, consisting of all rows, and then the fifth until the 8 columns. All right? So yun yung notations natin for algorithm 3. And also, this is what you can use in Matlab if you want to call certain parts of your matrix A. All right, so let's look at the householder algorithm. So the input is an m by n matrix. Okay, and the output is a unitary matrix Q, which is m by m, and then a right triangular matrix R, which is m by n. Okay. And then this is how we do the householder QR factorization. We iterate on K from 1 to n, so meaning we will iterate on each of the columns, okay? So we do it from K going from 1 until n. So papasadahan natin lahat ng columns. Okay, so if you have your specific K, or if you are on the Kth iteration, this is what you need to do. Step 1, we define a vector Y consisting of the submatrix of A comprised of the kth row until the mth row. So remember, the matrix A has m rows. So ibig sabihin, mula kay row K hanggang sa dulo, tapos kukunin mo lang yung kth column. So this will always be an m minus k plus 1 by 1 vector. Okay? So kukunin mo lang mula kay row K hanggang kay row M. Tapos kukunin mo yung kth column. That's what we will call our vector Y. And then we will call its first entry to be Y1. All right. So when you already have your vector Y, we will compute two things in step 2. We'll compute W and V sub K. Now, what would W be? W will be this guy. It's going to be the vector Y plus the sign of Y1. The sign of Y1 is simply equal to positive 1 if Y1 is positive. It would be negative 1 if Y1 is negative, and it will be 0 if Y1 is equal to 0. But usually we don't want Y1 to be equal to 0, so we don't want, so you can do elementary column operations to avoid Y1 being equal to 0, all right? So, but that's what the sign function is. Sign of Y1 basically harvests the sign of Y1. So it's positive 1 if Y1 is positive, it's negative 1 if Y1 is negative. And then you multiply that sign by the length of Y multiplied by E1. E1 is the first elementary vector of the appropriate size. So E1 is 1 on the first component and 0 elsewhere. Of course, we need to pick the right size for E1 depending on the size of Y. Okay. So basically, ang nangyayari lang dito ay we are altering the first component of Y. Okay? Because W will be equal to Y plus this guy. But this guy is a vector which is 0 except on the first position. Kasi this is a scalar, this is another scalar. We multiply it to E1, but E1, ano lang siya, elementary vector. that has 1 in the first component and 0 elsewhere. So, ina-alter lang natin yung first component ni y in order to get w. Okay? And then vk is just the normalized version of the vector w that we just computed. Okay? So in step 2, we're simply computing two vectors, vector w and its normalized version we call v sub k. Now, w doesn't have a label to it kasi dummy variable siya, pwede siyang ma-update every time kasi sa computations, hindi ko kailangang i-save yung value ni w. So okay lang na na-overwrite siya every time. But VK is different because I need to take note of what the VKs are for each of the Ks, kaya may label siya na subscript K. Kasi mamaya kaya kailanganin ko yung V1, yung V2, yung V3, and so on. Okay? Hanggang kay Vn. Okay, third step. Third step is we will update the matrix A. Remember, the matrix A is M by N. But at every iteration, we are updating certain parts of the matrix A. So, ganun yung nangyayari. Parang ina-update natin ng ina-updates in matrix A, and you will see later that at the end of the algorithm, the matrix A, the updated matrix A, will be a right triangular matrix. So, on the kth iteration, we will update the submatrix of A, starting from the kth row until the end, and the kth column until the end. So, paliit ng paliit yung ine-edit natin kay matrix A kasi at every step of the way, we are guaranteeing that we are getting a right triangular matrix. Okay. So, but how do we update that submatrix or that portion of the matrix A? We do that via this formula. Okay. So ito lang yung kukomputin nyo at every step. Well, let's see the terms on the right-hand side. V sub k, let's see what the size of V sub k is. Mention that V sub k depends on the size of y, all right? So what's the size of y? Y is, let's see, y is m minus k plus 1 by 1 matrix, right? So it's a column vector, okay? So that means this guy, so si actually si YA yon, so si VK ay ganun din. So VK is m minus k plus 1 by 1. And then we multiply it by its adjoint. The adjoint would be 1 by m minus k plus 1. So if we multiply this by this guy, so VK adjoint will be m minus k plus 1 by m minus k plus 1. It's going to be a square matrix. So again, this guy would be m minus k plus 1 by m minus k plus 1. So nakikita nyo, though mukhang komplikado yung householder, pero at every iteration, lumiliit ng lumiliit yung matrix na kinoconsider natin because the value of k is increasing, right? Palaki ng palaki yung k, so ito ay paliit ng paliit, so yung matrix na ina-update natin, paliit din ng paliit. So if vk times its adjoint is m minus k plus 1 by m minus k plus 1, I need to get the identity matrix of the appropriate size and perform this subtraction. So this guy would be m minus k plus 1 by m minus k plus 1. We need to multiply it by the matrix A. The matrix, or this submatrix of A. But this submatrix is, how big is this? This has dimension m minus k plus 1 by n minus k plus 1. So we can really perform the multiplication. So the product would be m minus k plus 1 by n minus k plus 1. And that would be the right size for this submatrix. So hopefully you see how the dimensions of the matrices here agree. So yung product dun sa kanan ay magiging m minus k plus 1 by n minus k plus 1, which is the same size as the submatrix that we want to update. Okay, so that's step 3. And then in step 4, we will just save this matrix HK, which is what we call a householder matrix. So yung householder matrix natin ay yung ginamit natin na pang-update dun sa submatrix, ilalagay ko lang siya dun sa pinakamababang diagonal entry. So basically, this is what we call a matrix in block form because all of the entries that you see in this block form are matrices themselves. So ito ay matrix. Alam natin siya ay size what? It is of size, it's square. It is size m minus k plus 1 by m minus k plus 1. So siya yung nandito sa anchor dun sa lower right-hand pivot ng matrix H sub k. So i-plug in nyo lang siya. And then yung HK dapat siya ay m by n. So ibig sabihin, kailangan ko magdagdag, kulang siya ng columns, kulang siya ng rows sa taas, magdadagdag lang ako ng zero matrix of the right dimension. So punuin nyo lang ng zeros yung ibabaw niya, punuin nyo lang yung zeros yung sa kaliwa niya, and then yung nasa diagonal niya, lagyan nyo lang ng appropriate identity matrix, kung ilan yung kulang, so that HK will be m by m. So, lalagay nyo lang yung I minus VK adjoint sa lower right hand pivot. Then, lagyan nyo lang ng mga zeros yung sa ibabaw niya. Lagyan nyo ng zeros yung nasa kanan niya hanggang makabuo kayo ng M by M matrix. Tapos, kulang ka dito, lagyan mo siya ng identity matrix. So, don't worry, I'll illustrate it later, but that's how you form the householder matrix. All right? And then after you have done these things, these 4 steps for every value of k, starting from 1 to the number of columns, you can now compute the unitary matrix. The unitary matrix is actually the adjoint of Hn times Hn minus 1 times H1. Kaya mahalaga yung pag-compute ng mga HKs every step of the way, because they will give us the matrix Q, and the final A matrix after all of those updates will be our right triangular matrix. Kaya ang sabi nila, the householder QR-factorization is an orthogonal triangularization, because the main output here of the algorithm basically is an updated matrix A, which is right triangular. Kaya siya ay kinoconsider ng marami as a triangularization. And we perform the triangularization by way of orthogonal matrices. So kaya siya tawag ay orthogonal triangularization. In contrast to the Gram-Schmidt process, which is a triangular orthogonalization. Kasi kung mapapansin nyo, in the Gram-Schmidt process, our main output is actually an orthogonal set, right? Or actually an orthonormal set. And we do that by the way of using triangular matrices. All right. So let's see the householder algorithm in action via example 66. Let's first do it by hand. Okay. So let's consider the matrix A. So this is a 4x3 matrix. And now let's apply algorithm 2 to find a QR decomposition for the matrix A. Okay. So here we have m equals 4 and n equals 3, the row and the number of rows and columns respectively. So the householder algorithm, algorithm 3, iterates on the columns. So ibig sabihin, we'll have 3 iterations. We do it for k equals 1, k equals 2, and k equals 3. Okay. So let's start with k equals 1. First step, we define the matrix Y, or the vector Y. Remember, the vector Y is the submatrix of A with the starting from the kth row until the mth row, and use the kth column. Plug those numbers in. We are on the first iteration, k equals 1, m equals 4, k equals 1. So as expected, this is a single column consisting of the first until the 4th row. So matrix A, kunin mo lang yung first until the last row. So ibig sabihin, kasali pa sila lahat in the running. But we are just considering the first column. So ito si Y. Okay, so first to fourth row, but first column. Okay, now that's y. And then y1 is the first entry, so y1 is equal to -1. So, na-define na natin yung matrix, yung vector y at saka si y1. Then we proceed to step 2, which is basically computing w and v1. Remember, we compute vk at every step of the way, right? Or every iteration. So what is w? Again, by formula, w is y plus the sine of y1 times the length of y times the elementary vector e1. Okay, so copy y over there. Okay, then again, sine of y1 is just basically what is the sine of y1? Y1 is negative, so that means sine of y1 is -1. Kasi kukunin mo lang talaga ano yung sign literally ni y1, and that goes here. Kaya nagkaroon ng minus sign dot instead of the plus sign from here. Because sine of y1 would be -1 times +1, so it's going to be -1. And then we need to compute the length of y2. Remember, the Euclidean length is just the square root of the sum of the squares. So -1 squared is 1, plus 1 squared is 1, plus -1 squared is 1, plus 1 squared is 1. So basically we have this square root of 4, which is 2. So that's how we got that. Okay, so yun. And then E1 is just the first elementary vector of the appropriate size. So for the vector addition here to make sense, E1 should be chosen to be the same size as Y. Y is 4 by 1, so E1 should have 4 rows. One non-zero entry at the first level, and then 0 everywhere. So yan lang yung mangyayari. Perform the subtraction, we get our W. Okay? And then W is not crucial, it's just a dummy variable or a dummy step. Ang kailangan talaga natin is si V1. And V1 is nothing more but the normalized version of W. So ino-normalize ko lang si W, meaning I will divide all entries in W by the length of W. By the length of W. Kasi pag kinompute natin yung length ni W, magkakaroon ka lang ng 9 plus 1 plus 1 plus 1, and that's going to be square root of 12. So i-divide lang natin lahat by the length of W. All right? So essentially, we get this as our V1. So take note of V1. We will need that in steps 3 and 4. Okay. Now we are on step 3. Step 3 is basically updating our matrix, A. Okay. So remember, in the algorithm, we were told to update A, or the submatrix of A, starting from the kth row until the mth column, from the kth row to the mth row, and then kth column to the nth column. So, ibig sabihin, ito lang yung parang lower right-hand pivot ng matrix A. So, anong ipapang-update natin? Unfortunately here, 1 to 4, 1 to 3, siya na yung buong matrix A. So, kailangan nating i-update yung buong matrix A at the first step. Okay. Now, how do we update that? We'll just use this formula. Identity matrix of the right size minus 2 times V1. V1 is this guy. V1 transpose can be easily, or V1 adjoint can easily be computed by taking the adjoint of this, right? Remember, ang adjoint niya lang ay 1 over 2 root 3 ng -3, 1, -1, 1. Okay? So the adjoint is 1 by 4. So this is 4 by 1, 1 by 4. You multiply them together, you get a 4 by 4 matrix. Scalar multiplication, so still 4 by 4. So here we need the 4 by 4 identity matrix. So this is 4 by 4. This is also this is 4 by 4. This is 4 by 3. So the result should be 4 by 3, which is an entire update for the matrix A. All right. So if you perform this operation or this multiplication, you'll get this matrix A. Okay. And this is the matrix A that we will use from now on. So forget the original matrix A. Ito na yung updated matrix A, and this is what will be passed on onto the next iteration of the algorithm. Okay. But before that, we also need to take note of H1, the matrix H1, which will be used to get the unitary matrix later. Okay. So H1 basically is identity 0, 0, and this would be I minus 2 V1, V1 transpose, or V1 adjoint. But we said this guy is, how big is this? This is already 4 by 4, right? 4 by 4 na to. So, but H1 should be 4 by 4 because it should be M by M, right? So H1 should be M by M. So si H1 kailangan by hook or by crook will end up to be a 4 by 4 matrix. So pero ito yung formula niya. But luckily, yung identity minus 2 V1, V1 transpose is already 4 by 4. So we don't need to add a row of zeros here, a column of zeros here, and an identity matrix here. Hindi na natin kailangang mag-add kasi ito ay 4 by 4 na. So we'll just copy that over. And this is your 4 by 4 matrix H1. Okay? And that's the first iteration. Before I proceed, any questions so far? I hope everything is good. Yes, Jeng?
Wait. So sir, nang sinabi niyong by hook or by crook, so meaning pag hindi siya nag 4 by 4, we just add 0 columns and 0 rows para
Yes.
mag-equal sila. So for example, if 5 by 5 yan siya, mag-a-add lang ako ng 1 0 0 0 at saka 0 0 dun sa taas.
Yep. So
Okay.
kung ina-expect mo H1 dapat ay 5 by 5, you're right. Mag-a-add ka dito ng zeros. Mag-a-add ka dito ng zeros. Mag-a-add ka dito ng identity. Pero ilan na lang yung kulang? Kulang ka na lang ng 1 by 1. Kaya 1 na lang yung ilalagay mo dito. So if you're expecting a 6 by 6 householder matrix, tapos meron ka lang 4 by 4, so magdadagdag ka ng dalawa dito para magkaroon ka ng 6 columns. Magdadagdag ka dito ng dalawa para magkaroon ka ng, magdadagdag ka rito para magkaroon ng 6 columns. Dinagdag ko to para magkaroon ng 6 rows, pero kulang pa ako dito ng 2 by 2, right? So para mabuo yung matrix, kailangan identity to. So yun yung itsura ng H1 if you're expecting a 6 by 6 matrix. All right? So you'll see this again in k equals 2 later. Kasi yung k equals 2 kulang na to. So kailangan ko mag-append ng 0, 0, and 1, 1. Yes, Marvin?
Sir, good afternoon.
Yes, good afternoon. Do you have a question?
Sir, yung sa step number 4, kasi kung copy lang siya galing sa step number 3, bakit po iba yung ano niyan?
Yung sa H1, ito yun. Ito lang siya. Yung sa step 3, na-multiply si itong factor na to, i-multiply mo dun sa submatrix na ina-update mo. Pero yung kay H1, ang ginagamit natin sa kanya ay ito lang. Tapos, etong first factor lang. Pero sa step 3, kaya ganito yung result kasi etong matrix na to, identity minus 2v1, v1 adjoint, is multiplied to the submatrix A that we need to update. So, pero sa step 4, ang ginagamit ko lang ay ito. Yung pinang-multiply ko kay A. Does that make sense?
Yes, sir. Thank you so much.
Yep. Yeah. So, kailangan ko yung mga HIs o yung mga HKs kasi yung HKs yung magbibigay sa atin ng matrix key. Alright? So, any other questions? So, mas interesting yung mga next cases kasi yung step 1, in-update natin yung buong matrix. Kaya medyo mukhang trivial yung mga nangyayari except for the lengthy computations. So let's try the second iteration. So tapos na tayo sa k equals 1. So let's do k equals 2. For k equals 2, step number 1, we define the vector y. And again, the vector y is the submatrix for A, consisting of the kth row until the mth row, but the kth column. So nasa k equals 2 na tayo. That's how I got that. M is fixed. M is the number of rows. K is equal to 2. So kukunin ko dun sa updated A, yung second to the fourth row, but just the second column. So tingnan natin yung matrix A na na-update natin kanina. Titingnan ko yung second row to fourth row. So ito yung candidates ko, second row to fourth row. Pero I'm gonna get the second column lang, so I'll get this. And that's how I get the matrix Y. Okay? So get the second to the fourth row, but just the second column of the updated matrix. So you never go back to the original matrix A. You go back, you only go to the recently updated A. So kaya ngayon, yung matrix Y ko, when k is equal to 2, will be 4/3, 2/3, and 4/3. The first element of which is 4/3, then that will be set as my Y1. Okay? Now, step number 2, compute two vectors, W and V2. So let's go to W. So it's going to be Y. So copy Y over there. And then sign up Y1. Y1, the first component is positive. So the sign of Y1 would be positive 1. So that's how I got the positive sign in there. Compute the norm of Y. So pag kinompute nyo yung norm nito, again, square root ng sum ng square. So that's going to be 16 over 9 plus 4 over 9 plus 16 over 9. I guess that's going to be 36 over 9 or 4. So this would be square root of 4, which is 2. And then put the first elementary vector of the right size. V is 3 by 1. So si E1 ako consider ko dapat may tatlong rows to have the vector addition properly defined. It's going to be 1, 0, 0. That's going to be my E1. And then perform the addition. You're going to get this vector W. But in essence, we don't need W, but we need a normalized version for W, and that's what we will store as our V2. So just compute the length of the length of W, and then divide all entries by that length. So I guess the length of W is what? I guess it is root of 120 over 9. Tapos, ni-reciprocate ko lang para maging multiplication, naging 3 over 2 root 30. And then because I'm doing everything by hand, I want to deal with small numbers. But essentially, if you do the simplification, you can write it this way. Okay. Though, if you are good at working with large numbers, pwedeng i-keep nyo to as 3 over root of 120. Then multiply nyo with this guy, so you'll get an equal V2, pero mukhang mas malalaki lang yung number kailangan yung paglaruan. So here I just simplified it this way, so I'll have smaller numbers to deal with. Okay. All right. So we have V2. We keep that in memory because I'll use that V2 in steps 3 and 4. Okay. So in step 3, we will update the matrix A. But this time, we will not update the entire matrix A because in step 3, we were told only to update the submatrix of A consisting of the k to the m row and the k column until the nth column. So ito lang yung ina-update ko. So remember, m is 4, n is 3. That doesn't vary kasi sila yung number of rows and column. So si k ay 2. So, ito lang yon. So, ibig sabihin, ang kailangan ko lang i-update, second row until the fourth row, second column until the third column. Okay? And how do we update that? So, we compute identity minus 2 V2 V2 adjoint. So, what is V2? V2 is 3 by 1. So V2 adjoint will be 1 by 3. So this product here, the subtrahend here would be 3 by 3. So we need a 3 by 3 identity matrix here. So this is going to be 3 by 3. This is what? This is 3 by 2. So we get a 3 by 2 matrix back. Okay. And then we said that we will update the matrix A or just a sub matrix of matrix A. So second row until the fourth row. So dito supposedly on. Tapos second column to the third column. So we're gonna update this. So ito lang yung portion na na-update natin. So yung hindi ko na box, yung 242000, galing sila dun sa latest matrix A that we have, right? So this guy was updated coming from the calculated submatrix here. Plug them in. And then yung natitirang entries, sila yung nanggaling dun sa matrix A from step k equals 1. Okay? So hindi ko pinakalaman to. Mula dun sa pinaka-latest na matrix A, ito lang yung in-update ko. Okay? Kasi you see here, mukhang satisfied na tayo dito kasi remember the goal for the matrix A is to get a right triangular matrix. 0 dapat yung nasa ilalim ng main diagonal. In the first update, we were successful. 0 na lahat ng nandun sa sa ilalim ng first entry. Now, in the second update, you will see na ito yung main diagonal entry for the second column and everything below it is already 0. Palapit na tayo ng papalapit dun sa right triangular form na gusto natin. Okay? So, this is the new updated A, and this is what is to be passed on to the next iteration. Okay? Now, of course, we will need H2, the householder matrix H2. Now, the householder matrix H2, etong matrix na to, ito yung pang pivot din sa lower right portion ng matrix H2. And again, we mentioned this is 3 by 3. Actually, if you do the computation, ito yung makukuha nyo na I minus 2V2 V2 adjoint. So yun yung makukompute nyo na 3 by 3 matrix. Dahil again, by hook or by crook, H2 should be a 4 by 4 matrix, right? Because it should be M by M. So kulang ako ng isang row sa taas, so dadagdagan ko ng puro zeros. Then kulang ako ng isang column, so magdadagdag ako sa kaliwa ng columns of zeros. And then makukulangan ako dito ng entry, kulang ako ng 1 by 1, so kailangan ko ilagay yung 1 by 1 identity matrix, which is just the scalar 1. Okay, so this is your second householder matrix. I hope the algorithm make more sense now that we saw a non-trivial iteration. Is that okay? Or do you guys have some questions? All right, I assume everything's well. So let's try step number 3, or the last iteration. Kasi remember, nag-iterate tayo sa number of columns. So medyo masakit yung householder algorithm if you have lots of columns involved, right? So, but of course, you don't want to do these things by hand. So, but I think I have a Matlab code to share with you with the householder transformation. So you can play with bigger matrices later. So here, third iteration, k equals 3. So for k equals 3, we will define the vector y. Again, vector y is the submatrix of A consisting of k to m, comma k. So here we have 3 to 4, comma 3. So third column, and then we'll borrow the third to the fourth rows of the updated matrix A. So if we go back to our matrix A here, ito yung matrix A, kailangan ko yung third row to third column, third to fourth row, and then third column. So we'll have 16 over 5 and 12 over 5. And that's how we got the vector y. Again, doon ka lagi sa updated matrix A titingin. Okay? Now we got our matrix, our vector y. First component is 16 over 5. I think mali yung notation ko. Ang notation ko dapat dito ay y sub 1. Okay, y sub 1 is 16 over 5. So we go to step 2, compute W and V3. So W is this matrix here. So copy, or this vector over there. Copy Y over. Y1 is positive, so we'll have a positive sign over here. The length of Y is equal to 4. And then this is the elementary vector, 1, 0, right? So because Y is 2 by 1, so we'll have E1 to be the 2 by 1 elementary vector, whose first component is 1 and all other components are 0. Okay? And then add them together, you get 36 over 5 and 12 over 5. But we're not interested in W, we want a normalized version for W. So that's why we need to compute V3. V3 is just W divided by its length. So computein nyo lang yung length ni W. Reciprocal na to nung length ni W kasi nasa denominator yung length ni W. So this guy will now be multiplied to W. Simplified version, you'll get this one. Okay? So this would be our V3. Now in step 3, we need to update. Ano nga yung i-update natin? We need to update K to M, comma, K. Dapat ba K yun? Let me just see. I think that should be, yeah. This is supposedly from K to N. Pero remember, N is equal to 3. So basically, K is 3, N is 3, so it's from 3 to 3. So sinimplify ko na lang third column. Okay? So, but first, let's check the matrix dimensions. V3 is 2 by 1. V3 star will then be 1 by 2. So this guy is 2 by 2. I need a 2 by 2 matrix here. So this is 2 by 2. And then this is what? This is 2 by 1. So we get a 2 by 1 matrix, which is what we want in our update. Okay? So compute this. You get -4, 0. And that will be the submatrix for A, or the new submatrix for A, starting from the third row to the fourth column and the third column. So basically, ika-copy paste ko to papunta dun sa susunod na step, pero kailangan kong i-update yung third to the fourth row and third column. So this should be updated. And you know that this should be updated because we are gunning for a right upper triangular matrix, right? So update nyo siya. -4, 0. So ito yung nabago. And then everything that is not boxed in this expression for the matrix A was copied over from the latest updated A from K equals 2. Okay? And then step 4, we get our householder matrix H3. Now again, this guy is the lower hand pivot for H3. This is 2 by 2. So if you will compute this guy, though hindi ko na siya napakita kung ano yung itsura nitong I minus 2 V3 V3 adjoint. But that's a 2 by 2 matrix. Actually, that is this guy. Okay? Ito yung makukuha nyo mula sa I minus 2 V3 V3 transpose. V3, yeah, okay, that's right. And then since by hook or by crook, H3 should be 4 by 4. I only have 2 rows and 2 columns here. So I need to add 2 more rows above it consisting of all zeros. And I'll need to add 2 columns of zeros to the right, to the left of it to get the 4 rows and 4 columns. But even after the addition of those zeros, I still lack a 2 by 2 matrix here. But again, it's in the diagonal to this pivot matrix here. So this should be an identity matrix, right? So I2 yung ilalagdag ko sa kanya. So this is our third householder matrix. Okay. And then now we can now build up our unitary matrix Q. Kasi tapos na yung iterations natin. We did all 4 steps for all columns of the matrix A. So we end up with a unitary matrix that can be computed as the adjoint of the products of the householder matrices. But remember that matrix multiplication is not commutative, so make sure you do it in the right order. So we do H3 first, and then H2, and then H1. Take the product, and then take the adjoint of the product. So you get this, and this is our unitary matrix Q. And then the latest or the last version of the matrix A would be our right triangular matrix. So 2, 4, 2, 0 minus 2 minus 8, 0, 0 minus 4, 0, 0, 0. Okay? So that's the householder algorithm for you. Maraming steps involved, but I hope with the algorithm, with a copy of the algorithm on your side, you can perform it manually. I think pinagawa ko yata to in one of the homework problems. I'm not just sure, but let's browse the homework problems later. But let's see. Now, I have included in the module package a Matlab script. And perhaps let's look at it. Sinama ko ba siya dito? Yes. Pero I guess it's you want to see it in Matlab. So let me share my Matlab screen here. Okay. So I hope you guys can see my Matlab screen. Okay, there you go. And then this is in ex66.m. So let me open that. Okay. So, all right. So this is the householder or the implementation of the householder algorithm. Okay na ba yung size or you want me to make it bigger? Nung tinitnan ko yung recordings natin, saka ko lang napansin na baka maliit masyado yung size ni Matlab kapag ka nag-share ako. But let's see. Let's increase it to 18. Okay. So this is an implementation, a Matlab implementation of example 66. Okay. So first, you need to input your matrix A. So again, this is the same matrix we used in example 66. And then I have here in line 4 the householder function. Unfortunately, the householder function is not intrinsic to Matlab, so I need to write an internal function for the householder algorithm. So kung kailangan yung gamitin or gusto nyo gamitin itong householder algorithm ko, you need to copy the internal function that you see in lines 12 until 42 dun sa dulo ng Matlab script na gusto nyong gamitin. So kung gusto nyong sumulat ng sariling Matlab routine, tapos gusto nyo na lang gamitin itong householder function na dinefine ko in this code, kailangan nyong i-copy-paste yung lines 12 hanggang 42 sa dulo ng Matlab script na gagamitin nyo. Right? So that's how internal Matlab functions work. Pwede siyang external pero I don't want to go to the technicalities of Matlab. So kaya internal functions na lang yung ginamit ko. All right. So bulk of the work will be done by the householder function I defined in the end of this script. Pero what the householder function will give us, it will give us two things. It will output a matrix Q, which is the unitary matrix Q promised by the algorithm, computed as the adjoint of the product of the householder matrices that came from our algorithm. And then R is the right triangular matrix. Okay. So basically, yun lang. Tinawag ko lang si householder. Sabi ko yung result, tawagin mong Q and R. And then line 6 and 7, I just want Matlab to display Q. And then in lines 9 and 10, I just want Matlab to display R. So let's see. Let me hit F5 para mag-run yung algorithm. And we see here the output. So the I just Sinabihan ko pala si Matlab to output the matrix A just for me to make sure that I have the right matrix A, or I have encoded the right matrix A. And then the matrix Q is this. Or sorry, iba pala to. Tama ba? Parang iba pala to sa example 66. Parang ito yata yung nasa homework nyo dapat or something like that. Sorry, so baguhin ko siya. Hold on. Comment this guy. And then let me retype the matrix A. The matrix A should be -1, 1, 1. And 1, 3, 3. And then -1, -1, 5. And 1, 3, 7. And then hit F5, hit F5. Okay, yeah, I think this is right. So ito yung 4x3 matrix ng example 66. So paki-check pala yung example 6, yung ex66.m. Hindi ko yata na-revert yung matrix A. So makita nyo naman dun sa handout ano dapat yung itsura ng ex66.m. Siguro when I was playing with this, or I'm trying to see results from your homework, probably I changed A and forgot to save it back to the original given from example 66. But this is how it should go. And then the matrix Q is this one, which is basically, I think this is what we got from doing it by hand. So yung -1/2, -1/2, 1/2, 1/2, and so on. Though I don't know if Matlab computed it exactly. So pwede tayong pumunta sa workspace. So depending on your Matlab version, you'll see a workspace here. So makikita nyo yung mga variables na defined. In my case, ito yung nandito sa kanan. So sa workspace, I can click on Q to see the matrix Q displayed. So ito yung matrix Q daw. Gusto ko lang makita kung eksakto. Kasi pinapakita niya, si Matlab nagpapakita ng 4 decimal digits by default. So when you see -0.50000, so meaning this is up to machine precision. But if you see halimbawa 1, Matlab knows it's exactly 1. Pero pag sinulat ni Matlab na 1.0000, that means merong decimal digits na susunod. So hindi eksaktong 1 yung nakuha ni Matlab kung ang i-display niya ay 1.00000. Pero pag in-output niya ay 1 lang without any decimal points after it or decimal digits after it, ibig sabihin eksaktong 1 yung nabasa niya dun sa input. Okay? So let me just check yung eksaktong 1/2. Say first row, first column ni Q. Para makita niya, pwede niyong i-copy yon. So go click that entry. So kinlik ko yung 1/1 ni Q. Kasi pe-paste ko siya sa workspace. Para makita kung ano yung actual value na compute niya. And you see here, it's -5 followed by a bunch of zeros. So it looks like Matlab was able to compute the first entry of Q to be exactly -1/2. So tingnan ko nga ito, nasa 4th row, 2nd column. Copy, Control C, and then Control V on the command window, and it looks like na-compute niya rin exact. So I don't know what happens toward what happened towards the end, pero mukhang up to machine precision, it's equal to -1/2. So that's a good sign for us. And then let's look at R. R is this guy. So you see here, Matlab did not just display 2, but it displayed 2.0000. So chances are hindi eksaktong 2 yung na-compute ni Matlab, because remember again, Matlab rounds off probably on the 16th decimal digit every after the operations. So bawat isang operation nag-round up siya to 16 decimal digits So kaya baka hindi eksakto yung makukuha nating sagot. So let's check. Again, I'll double click R coming from the workspace. Oh, mukhang yung first entry nakuha niya is exactly 2 kasi dito sa workspace variable for R, yung second row, first column ay 2 niya din-display. Second row, first row, second column, exactly 4 niya din-display. First row, third column, eksaktong 2 niya din-display. I-copy-paste ko nga to sa workspace just to see what happens. So you see here, after copy-pasting that entry, 2 yung in-output ni Matlab. So na-compute niya eksakto yung first row, third column to be 2. But if we go, say, to the third row, third column, which Matlab displays on the workspace as negative 4.4 zeros, pag kinapi-paste ko kaya yan, ano itsura niya? Well, it still is displayed up to exactly negative 4, at least in the amount of decimal digits allowed here. So mukhang maganda talaga yung approximation niya. Though it might not exactly be 4 in memory, but it's good up to this number of decimal digits. And then we said that, or we promised that R should be an upper right triangular or an right triangular matrix. So supposedly lahat ng nasa baba ni 2 dun sa first row, dun sa first column, the entries on the second to the fourth row should be 0. But you see here that Matlab only has them as something times 10 to the minus 17, something times 10 to the minus 17, and something times 10 to the minus 16. Again, Matlab by default works with machine precision 10 to the minus 16 or a factor of that. So whenever you see a number that is smaller than 10 to the minus 16 or around that number, it's almost equal to 0. Okay. So if you look at the second column, third and fourth rows, again, 10 to the minus 16, 10 to the minus 17. So from the machine point of view, this is as close to 0 as we can get. But you see here, third row, fourth column, fourth row, third column, we get a 0. So ibig sabihin, eksaktong 0 yung na-compute ni Matlab sa kanya. Okay. So let's check if we got a good factorization. Okay. So laging dalawang bagay yung titingnan nyo. Maganda ba yung factorization na na-compute natin? Again, the promise is that Q times R should be close to A. So to check how close the QR factorization is to the intended result, so I will compute the norm. So naran ko na si ex66.m. So meron akong mga variables sa workspace. So this variables has values. So I can call any of them in the command window and Matlab knows where to get them. So I will measure the norm of the residual. So I'll have norm of what? I want Q times R. And I want to know how far it is from the matrix A. Again, the promise is that A is equal to QR. So to measure how good this factorization is, so we need to subtract A from QR and find the size of the result. So ito yung size ng error. So the size of the error is 2.8815 times 10 to the minus 15. So basically, it looks like it's a very good approximation. Kasi napakaliit ng residual, right? So if you want to talk about percents, kasi medyo relative din yung measure ng kalaki yung error, tama? So here you can think of it as, dito kasi walang masyadong problema kasi the norm of QR minus A is 10 to the minus 15. So virtually, from the machine point of view, this is almost equal to 0. But if you want to talk about percents, so ilang percent yung error, you can take a look at the relative error. The relative error is computed by the error divided by the norm of the expected result. So yung numerator ay norm ng QR minus A. Ito yung norm ng residual, gaano kalaki yung error, divided by ano yung expected answer. Relative error, or you can interpret it as the percent error. So if you compute that, you see that the percent error is about 2.99 times 10 to the minus 14%. So ganun kaliit yung error. Usually we prefer to use relative errors instead of the norm of the absolute error. Kasi pagka nagdidepende rin dapat yung measure of error, how big is the thing that you are computing. Kasi halimbawa, nagsabi ka lang ng halimbawa, 9,999 minus ang expected mo ay 10,000. So pag kinumpute mo yung error, ang error ay bakit mali? Ako lang na isang zero. So, halimbawa, meron kang 1,000 minus 999. Kukunin mo yung error, right? So, pag kinuha mo yung error, ang error ay 1. Pero you don't know if 1 is big or small. So, this is the residual. So, sabi ang error ay 1. Pero you need to contextualize that into the problem. Ano ba yung mini-measure mo? Kung ang mini-measure mo yung error na 1 against is say 1, that's 100% error. Pero kung mini-measure mo siya again, just in this case, so kunin mo yung relative error. So ibig sabihin, you have a relative error of 10 to the minus 3, and that is about 0.1%. So kaya usually mas okay na measure of error yung percentage error. Kasi kina-contextualize mo siya on how big is the thing that you are measuring. All right? So kaya in the homework, it might be better to compute the relative error para ma-contextualize nyo siya to the size of the thing that you are measuring. Okay? Now, but that is just one measure. Again, what we did is to measure how good the QR factorization is. And we said the QR factorization is good up to 15 decimal digits. That's good. But another thing that we need to measure is how close to a unitary matrix the result Q is. Kasi again, ang promise ng QR factorization, we get the QR factorization where Q is unitary. So another check to do is to see how big or how close to being unitary Q is. All right? So ano nga ba yung property ng unitary matrix? So sabi, ang unitary matrix, dapat ang inverse niya ay yung adjoint niya. Okay? So that means the adjoint times the matrix Q must be very, very close, ideally, within machine precision, to the identity matrix of the right size, right? So what I'll do here is to compute Q adjoint. Remember in Matlab, Q adjoint is Q prime times matrix multiplication is just a star or an asterisk times Q. And then I will compare it against the identity matrix. Ang identity matrix sa Matlab ay I. Of how big is the matrix you are expecting? The matrix Q is 4 by 4. So we need the 4 by 4 identity matrix. And then ending parentheses for the norm. Divide that. So we get 2.9962 times 10 to the minus 16. So this tells us that, yes, what we got is a very good unitary matrix because it is very, very close to being unitary. It is actually within machine precision. So whenever using Matlab, when you see when you see that the norm of the error, the absolute error, is a factor of 10 to the minus 16, then you can say, yeah, virtually it is correct. So that's the best we can get out of Matlab. Okay, so that's how you calculate. Yeah, these are the two important things to check in any machine implementation of a QR decomposition or a QR factorization. First, see if you have a good QR factorization. That is, see how far QR is from A. And second, try to see how close to a unitary matrix have you computed. So dapat yung Q adjoint times Q dapat ay napakalapit sa identity matrix. All right. So yeah. Okay, and I think that's it for the householder algorithm. Any question before I switch back to the notes? Any questions? No questions about that. Let me end this. Okay, so I guess this would be a good place to stop. And I think we are on track to finish the module on Wednesday. I was thinking to offer kung gusto niyo ba tapusin na natin ngayon, or let's take our time and just meet again on Wednesday to finish module 6. Kasi nakakaano na ba tayo? 1.5 hours na. So I guess we can stop here. Is that fine? And then let's just meet again on Wednesday to finish everything up. So yeah, but let's end with looking at the homeworks. Tingnan natin kung meron na kayong pwedeng matapos or simulan from the homework, because the last topic is about how to apply QR factorization to solving linear systems. We can easily do this in an hour probably. Yeah, let me just browse down to the homework. Meron pa pala pseudo inverse na sinabi doon. So anyway, so let's take a look at it. So I think you can do number 1. I just created the submission bins late yesterday or early this morning. So you can now submit to homework 6 if you already have them. Okay. Number 2, number 3. Okay, I think you can do part of homework 2 because I want you in problem 2 to solve the following system by hand by the householder QR factorization. So the thing here is that when I say solve this by hand, kailangan yung i-perform yung householder QR factorization by hand. So you need to follow the hand solution I have for example 66. What's the point of asking you to do something manually wherein we already have a Matlab code for it? I think it's doing everything by hand, at least for small cases, is a good exercise or is a good way to understand the algorithm. Kasi kung babasahin mo lang yung algorithm, hindi mo parang may imbibe by heart kung ano yung nangyayari dun sa loob ng algorithm. So even for me, if I want to do or I want to solve a big problem and I want a MATLAB implementation for it, I do not go to MATLAB and write a code for that thing. Ginagawa ko muna siya yung first few iterations on paper for a small example for me just to know exactly how the algorithm should flow and para malaman ko exactly in my mind how should it go, and then it helped me to have a clearer mind in encoding that algorithm. So in example 2, I want you to do the householder factor para
Sir, nawala po kayo ulit.
Okay, hello guys. Am I back? Ayan, mukhang nakabalik na ako. Tama ba? Okay, yan. Balik na rin yung computer ko. So let me see. Let me go back to Notability. Ayan, hold on. Okay na to. Okay. Yeah, I was just saying on I'm asking you to do the calculations in the calculations for the householder factorization by hand, because I want you to get a first-hand experience on how the algorithm works. Because I guess the best way to learn how an algorithm works is to experience it first by hand. So even if I'm writing, say, a Matlab code for a certain algorithm, I always practice doing it by hand first, at least for small examples, first few iterations before going into Matlab and writing a program for it. Because doing it by hand will give me a better understanding of how the algorithm should flow, right? So even though in problem 2, I ask you to do the factorization by hand, you can use calculators in the intermediate steps, but try as much as possible to use exact values. So kung meron calculator that can output fractions instead of decimal approximations, or if you have a solver that can output radicals instead of decimal approximations. So yung mga tipong square root of 3, mas maganda na i-keep nyo as square root of 3 para dun sa final answer instead of using an approximation 1 point something for square root of 3. All right. So you can use calculators, but I want to see the steps being done by hand. So bawal kopyahin lang yung manggagaling kay Matlab pag ginawa niyo yung householder para dito. Okay? So that's why I said this homework might take a little bit of your time, not a little bit, but more of your time. But at least you will spend you'll spend most of the times on pen and paper. Di siya kasing hirap ng homeworks 1, 2, or 3 na most of the work will be done in your head thinking of what would be the next step in the proof and so on. So this is mechanical, but it will take some time. So I hope you can start as soon as possible. So I guess here you can start getting a QR factorization for A. And then, yeah. And then the next step is to use the QR factorization into solving the linear system AX equals B. And the use of the QR factorization in solving linear systems will be our topic for Wednesday. And that would be our last class for the semester, if we will be able to finish the entire module 6. But if you got bored, you already finished that first half of problem 2, then you can go ahead, read the rest of the module. I think it's self-explanatory naman, so you guys can read the rest and then yeah, do the other half of problem 2. Problem 2 is worth 7 points. There are lots of follow-up questions here, so make sure you answer all the questions in the homework. Hindi ko na siya in-itemize. So, halimbawa here, yung mga typos pa yan, parang late in the day ko na siya na nagawa. So, wala dapat question mark doon. So, for instance, you need to say, kailangan nyo ikwento is X house accurate? So, there's a suggestion here how you can quantify being accurate. So once you call your solution X house, you need to answer, is this accurate? And then there's a suggestion here, how can you describe the accuracy? So you can check by computing via Matlab this ratio, which is the percentage error. Okay. So kailangan yung sagutin yung mga questions na yan, questions na to, and questions na to. So don't forget to answer any of those questions. And then may isa pa pala akong typo rito sa taas. Hindi ko matandaan kung saan. Pero I think I mentioned something na unstable. Dapat walang D. So dapat siya ay unstable lang. I forgot where exactly it is. But kindly correct that. So yeah. But hopefully, kapag ka hindi masyadong marami yung magsasubmit ng mga past due, at the last week of classes, I'll try to give this a proofread and try to upload an edited version of the entire module para at least you can have a close to I don't know, I'm close to perfect, pero isang module that is konti na lang yung typo errors. So hopefully no technical errors and just a few typos. Yun yung goal ko as a souvenir for you for this course. All right. So yeah, I guess that's it for now. It's a good place to start, to stop. We have less than 2 hours of discussion today. Unless you guys have some questions. No questions or clarifications? So yeah, I guess that's it for today. Thank you all for coming. Enjoy the rest of your day, and let's see each other again on Wednesday. Bye, everyone.
Bye,
Thank you,
sir. Thank
sir.
you.
Bye,
Bye
sir.
po.
Thank you po.